Hello everyone. Very good afternoon. We welcome you to our this webinar. We are very glad that all of you can make it to this webinar. We'll quickly brief out through the introduction session, and then I'll let you know that what the agenda is as per the time being. Let me introduce myself to you all. I'm Abhimanyu Singh, founder Solar Study. We'll be going through the introduction session first, and then we'll go through the body of the title, that is distributed generation in solar PV, and then we'll wind up with the Q&A session. So let me brief you through the agenda first, and about the about solar study, that what we do at solar study, and let us start with the webinar. So solar study has been founded in 2019 June, and since then we have progressed. In October 2019, we have got NAPSA PVA registration, that is North American Board for Certified Energy Practitioners. In November 2019, we had won. We have won a title of Super 30. That was around, like, we have came in top 30, top 50 startups in India in 2019 from awarded by Times Next. In December 2019, we had conducted our first NAPSA PVA batch, that was widely known as SSF, Solar Study Fellowship. In that, we have received candidates from UNDP, Nepal, then IIT Bombay, UC Berkeley, TÜV Rheinland. So these were some of the profiles that we had received, and till now we have our students, 6 to 7 of our students getting certified from South Asia, and more from like Oman, India, and Nepal. In April 2020, Solar Study has become a complete online marketplace, which is a platform where teacher or widely known as instructors can publish their online courses and interact with students live. Students can learn the online courses and get the certification in solar energy. So let me brief you through our speaker's profile for this webinar. Today's speaker for distributed generation in solar PV energy is Jeevan Kumar Malik. He's an electrical engineer from Institute of Engineering, Nepal, from 2006. He's an MTech in power system from IIT Delhi in 2011. He has been engaged in Schneider Electric in the capacity of senior engineer. And in 2013, he moved back to Nepal, and since then he's working with UNDP with renewable energy for rural livelihood program in capacity of regional energy officer. So he's been an expert in policy building in solar PV energy, whether it is utility scale, commercial rooftop, or residential rooftop. He's also been engaged in small PV, hybrid hydro plus PV plant arrangement in the capacity of policy builder. So we'll quickly overthrow about the webinar agenda. Since we had stated a time of half an hour, but adding the Q&A, it will have a run time of 45 minutes. So firstly, we'll discuss why distributed generation, why is the need for it in 5 minutes. Then we'll be discussing the advantages of distributed generation over centralized generation. We'll start till 5 minutes. Then the commonly known business models in DG will be discussed in 5 minutes. Then we'll take a case study of grid interconnected micro hydro in Nepal. That will stretch till 15 minutes, and we'll be opening the webinar for Q&A in the next 10 minutes. So this was all about the introduction for the webinar, that how it has been structured. More importantly, we'll also be generating certificates for the attendees. So we'll be sending the links by 5 o'clock today evening for the certification, which will be sent via email to all the attendees. So let us welcome Jeevan Kumar Malik, today's speaker, to carry forward the topic and light us upon some of the introductory factors from DG in solar PV energy. Yeah, hi Jeevan.
Hi Armenu, could you confirm my audio and screen sharing?
Yes, your screen is visible to us, Jeevan, and audio is also pretty much audible. You can start with the webinar.
Thank you so much, Armenu, for kind introduction. Hi everyone, very good afternoon all of you. As introduced by Armenu, I am Jeevan Kumar Malik. I am working in Renewable Energy for Rural Livelihood Project, RERL project, which is a joint project of Government of Nepal, AEPC, and UNDP in Nepal. Currently I'm working as a capacity of solar power expert, but however, I am also giving input to the grid interconnection of renewable energy projects. So in today's webinar, I will be discussing about distributed generation, which is a future for clean and reliable energy. And the detailed agenda has been shared by Abhimanyu itself. So if you see the history of the electricity in the world, very initially, before 1950, there was a concept of kind of a prosumer, producer and consumer itself. The concept of electricity comes from the very DC, that Michael Faraday's law, and then in the very beginning, the electricity was used for only for the lighting. And then in the era of 1950, 1940, 1950s, the diesel generators were coming into the market, and that was again limited to the few vicinity, like distribution in a village or a hamlet or in a community, but it was limited to some extent only, not like grid expansion or something like that. So in like early 1950, there was a 481 number of distributors alone in the UK itself. So then after nuclear era coming after the 1950, in around 1970, then the concept of this centralized generation comes, like thousands of megawatt or even hundreds of megawatt of nuclear generation, which is far from the load center, generation at one end and consumption at one end. And in between there is a long transmission lines. So this kind of concept has come, and currently I would say that this current decade 2010 to 2020 currently. So people talk a lot about this distributed generation, which is a generation at the vicinity of the load center itself, which is a grid connected system at the vicinity of the load center. And it's not like thousands of megawatt. It's far from the consumer, and consumption at one end and generation at one end. It's not like that. It's a distributed generation, which is in the vicinity of load center, and which has some advantage. I will be discussing about those things. And also this distributed generation, which is quite popular with the renewable energy technologies like solar, wind, and small hydro systems. And it's a prosumer, producer as well as a consumer, like net metering solar PV in your rooftop, solar in a rooftop. So that means you are producing energy from your roof, and you are consuming itself, and you are exporting your surplus energy to the grid. That's a kind of distributed generation. So definition first, let's go through the definition of distributed generation. According to IEC, that's International Electrotechnical, according to IEC vocabulary, the generation of electric energy by source which are connected in the power distribution systems. Usually the power generation systems are connected in the transmission systems, 132 kV, 220 kV, 400 kV or 765 kV systems, transmission systems. However, if you are connecting your generation system, solar, wind, or even a small micro mini hydro power into distribution line like 400 volt or 11 kV or 33 kV, that's called distributed generation. That's a definition of IEC vocabulary. And according to KTH University in the Sweden, Royal Institute of Technology. They have also similar kind of definition. Electric power sources connected directly to distribution network or on the consumer side of the meter. Like if you are generating solar PV in your roof and it is connected to your behind the meter, it's also a distributed generation. So sometimes dispersed generation, embedded generation, or decentralized generation, or distributed decentralized generation. These are the similar terms, I would say, that synonyms of the distributed generation. This is the one resource I am taking from renewable energy, reneweconomy.com.au. This is Australian newspaper, and this, in fact, this has been published in 2016, and this has astonished many of the RE professionals. According to them, this is one of the strategies of the utility in Australia, Horizon Power. So they have a roadmap of this centralized and distributed energy resources and stand alone. So just for common understanding, centralized generation means grid connected system of typically few hundreds of megawatt far from load center. And distributed generation, grid connected system of typically few hundred kilowatt near the load center. That is the biggest difference. Centralized generation is far from the load center, and distributed generation in the vicinity of load center. And a standalone system is of grid system, which is in the vicinity of the load center. There is no connection between the grid. However, in the distributed generation, the systems are connected to the grid. So they have like this roadmap in 2016. They have a centralized generation of like 98%, and distributed generation very little and a standalone. However, in 2025, their roadmap is a distributed generation of 53%, and in 2050, by 2050, they will have a distributed generation of 82%, and centralized generation just 9%, and 9% of standalone systems. This is their roadmap. So you can see the importance of distributed generation, how the distributors, electricity utility companies are giving priority to the distributed generation. And why distributed generation is important? First and foremost thing is we are utilizing our indigenous resources, local resources. If like we have a water stream or a small river and water is flowing, why not to generate power there itself and providing electricity access to the nearby community rather than importing electricity from long transmission and distribution lines. So this is first thing is we are utilizing local resources, and obviously the transmission line efficiency is going to increase. That means low transmission and distribution losses. And another thing is that we will have a low capital investment, low capex for the T&D line. So T&D line, if you are designing transmission distribution line, that all depends upon how far you are transmitting power and how much power you are transmitting. So let's say if you are producing some power in the village itself, there is no need of importing that much of power from long transmission distribution line. So sometimes instead of 33 kV line, it's even 11 kV line is an optimal system. So that means you are minimizing your investment by using 11 kV system instead of 33 kV systems. And decrease cost of consumers. If you are minimizing transmission distribution losses and capital investment in transmission distribution lines, definitely the levelized cost of energy which you are producing in your vicinity, that's definitely it will be cheaper. And obviously the bottleneck of transmission distribution line will be decreased. Sometimes like voltage sag or swell, or even sometimes transmission distribution line have a capacity constraint. So those limitations will not be there if you are using distributed generation. And decreased emission, if you are using solar, wind and small hydro systems, definitely emission reduction, there will be emission reduction. So for probably you might be knowing that power sector alone contributes to 2/3 of emission carbon dioxide emission in the entire GHG emission portfolio. So if you will be moving towards the renewable energy, definitely we will be contributing somehow in the emission reduction also. And in the last and most important is security and diversity. So let me explain the diversity first. We have seen that even diversity portfolio is equally important whether you are doing some business or you are power developer. Like even I can give you example like General Electric. They produce even aeroplane parts to LED lights to hospital equipments. They are diverting their portfolio. So the similar thing happens in the power generation also. If you are diverting, if you are only using one systems like a nuclear or maybe a thermal plants or maybe the hydro, that's not very energy secure systems. Like in 2015, we had a massive earthquake in Nepal. So if we had only hydro systems, hydro is you know that hydro is a much more civil structure and civil structure dependent. So if the magnitude of the earthquake is much higher, it's a massive destruction in the hydropower systems itself, and that may lead to a complete power blackout in the country. So at the same time, if we have some solar systems that have a very less civil structures, so that may not be severely impacted as a hydropower by some natural disasters. So that kind of power diversification is required in the energy portfolio itself. That will lead to energy secure nation. So that's a power generation mix, and if we have a distributed generation, that if there is an outage of the grid, we can operate that distributed generation as an islanded operation mode also. However, this distributed generation poses some technical constraints. For example, interconnection regulations. So first, when you will be approaching with your utility that I want to connect 50 kilowatt of system or maybe 500 kilowatt of system into the distribution line, maybe 400 volt line or 11 kV line, definitely your utility will be some hesitant, and they will be asking you several questions. They will definitely put some obligations that these will be the consequences, how you will be meeting. So it's obviously whether it is India or Sri Lanka or Nepal, all the utility people have the same response. So first thing is that if the distribution systems, these are mainly designed for the consumption only, not for the injection of the power generation. So if you are generating some power and injecting into the distribution line, definitely there will be some technical problem. So you have to mitigate those kind of problems. So first thing is that you have to be a very clear regulation for the distributed generation, and obviously it should be in coordination with your utility. And also the like net metering policy, some country and some state had a very good net metering policy, and still some country in the South Asia and Southeast Asian region is still yet to implement net metering policy and yet to implement the net metering projects in their country. But I would say that net metering, if you will be implementing net metering or any distributed, we have seen the advantages which I already talked. And another technical constraint is low inertia of inverters, whether it is a solar or wind. Definitely, we power system engineers talk about the inertia of the generator. Compared to hydro generator or thermal generator, these inverter has a very low inertia constant. So if in case of during some momentary fault, maybe a three-phase fault or single phase to ground fault, some kind of fault, so there is definitely there will be disturbance in the power system. So at that time, frequency ride through and low voltage ride through capacity should be provided by these generators. If you are using inverters, their fault ride through capability and low voltage ride capability are low compared to others. So definitely, if you are giving option of solar connecting to the distribution system and hydro connecting to the distribution system, hydro is obviously choice for the for the utility people. Another is a intermittency. It's a quite well-known effect we have discussed. So intermittency of the renewable like solar and wind, if you are injecting into the distribution system, it's all depends upon the weather and climate. Sometimes like small variation in the weather condition that may lead to a small signal instability in the grid, and that's a very serious concern to the power system operator. And another is distribution system restructuring. As I said, that distribution systems are mainly designed for the power consumption, not for the power evacuations. So, for example, here one diagram is just showing that if you are connecting one generator into the distribution system, and distribution system has some protection systems and relay, numerical relay or any control and protection systems, these relays setting for the some kind of fault here, which is not set as per the current contribution by this distributed generation, this G. So if you are injecting some current through this generator, some kind of arrangement need to do here in the relay itself. Relay setting need to change. So this kind of things need to rearrange if you are connecting distributed generation into the distribution system. And also some kind of, sometimes the conductor, ACSR conductor, that may not be capable to handle that much of power evacuation into the distribution systems. So these are the some technical constraints for the distributed generation. Let me go through the case study. In Abhimanyu shared that I will be talking about that business model also. I have incorporated business model here in the case study itself. So this is a transition from a standalone system to distributed generation. That means a standalone micro hydro system is connected to the distribution systems. That means national grid, connected to the national grid. So APC has experience of more than 24 years. And based on these long experiences, now we have realized that this distributed generation and grid extension is a most viable approach and best approach for reliable and quality electricity supply for the socio-economic development of the rural area. So this report we have initialized in 2011. So at that time we do not have any regulation, any policy to interconnect micro hydro system into the national grid. So we started advocacy with the utility, that Nepal Electricity Authority utility in Nepal, and it took around 3 years to convince them that there is no threat of interconnecting micro hydro system into the national grid. We have prepared technical standard, and that joint working committee was formed between utility and we. So we rectified all the issues, technical issues, commercial issues, and at the end in 2014 July, we have a policy for interconnecting micro hydro system into the grid. And again, it took 2 years to have a first power purchase agreement of this micro hydro system of less than 100 kilowatt system. In fact, there was some ambiguity in the language. So it took around 2 years to clarify that again for that ambiguity. And the first PPA has been concluded in 2016. And the first interconnection happened in January 2018. Again, in between this, we have some different technology. We did develop a new technology and then interconnected the micro hydro into the grid. So development of technology itself took around 2 years. It's not a ready-made kind of things like buy a grid type PV inverter system from the market and just interconnect into the grid. So micro hydro system is a little bit different. I will be talking about the technology part also. So this is a technology. In fact, you might have heard about this governing technology of hydro systems. There is a flow control governors. Simply, it's a commonly known as a governor only. So we didn't employ that governor into our micro hydro systems. We have an electronic load controller, ELC, which works as a governor. And let me tell you that this ELC, which is 10 times cheaper than the flow control governor, which is deployed in large hydropower systems. ELC just costs around $200. maximum $200, whereas the flow control governor, it will cost around at least I would say that $30,000. Sorry, $3,000. $3,000. So you can compare the 200 cost of ELC versus $3,000 of flow control governor. That is the only reason we developed own technology, electronic load controller technology, and then we interconnected micro hydro system into the grid. So these are some block diagram, turbine and coupling system, generator. We sense the frequency compared with the reference frequency and some proportional integral controller, and that generates the power switching device here, thyristor and SCR, and that diverts the power. Some power generation is a constant. If the consumer load is a constant, I mean, if consumer, let's say if my micro hydro system is 100 kilowatt and consumer load is only 60 kilowatt, the 40 kilowatt is diverted to dummy load, which is just heating the water at the powerhouse itself. So this is the control strategy for the ELC. And for the grid interconnection, when the micro hydro system is interconnected to the grid, we just deactivated the ELC, and when there is some outage in the grid and some disturbances in the grid, again the ELC comes into action and divert all the power generated to the ballast load, that is a dummy load. So again, we carried out some technical kind of a study, simulation, MATLAB simulation, to see the impact, technical impact of this grid interconnection of micro hydro systems. It's all the simulation results came satisfactory, which is agreed by the utility people also. Only some impulse has been seen here during the three-phase fault. I don't want to go into much detail into this simulation result. If some of you are interested, we have also published one paper into the IEEE, which is a very well-known publisher in electrical and electronics field. IEEE, you can find micro hydropower in Nepal, a journey from a standalone system to distributed generation. There you will find all the technical stuff related to this micro hydro systems. So in terms of financial aspect, we carried out the financial analysis, which is also important for the commercial terms for the PPA. So for the different micro hydro systems, 23, 50 kilowatt, 75 and 100 kilowatt systems, there are different plots. This is a blue for 23 kilowatt, 50 kilowatt for red, and green for 75, and purple for 100 kilowatt. Sorry. And IRR is plotted here in y-axis, and this is a distance between grid and renewable energy system, micro hydro systems. That means sometimes grid distribution system, that 11 kV system may be far from your power plant, sometimes maybe to 1 kilometer, 2 kilometer away, and that lead to that's a very crucial parameter to have a financial attractive of the project. If let's say if it is 3 kilometer away, and if you are connecting just 23 kilowatt of systems, that may not be quite attractive. The IRR is just 11%. And at the same time, if it is of 50 kilowatt system and we are connecting 3 kilometer away, the grid is available 3 kilometer away, then it may be a very attractive system, but that IRR is very high. Similarly, payback is also reflected here. So this is the impact we have seen from the first piloted micro hydro system connected to the grid. This 23 kilowatt of micro hydro system, that is distributed generation. So we have seen that this is based on the real case we have observed in the power plant. So by injecting this 23 kilowatt system into 11 kV feeder line, the voltage of distribution line increased from 370 volt to 382 volt. You can see the impact of this teeny generator. This 23 kilowatt of micro hydro system can boost up distribution system voltage of from 370 volt to 382 volt. The 12 volt of increment in the distribution system. That's a very good thing. And definitely we haven't carried out the distribution loss minimization. Definitely if you are injecting 23 kilowatt system into the vicinity of the load center, that in the village itself, no need to transmit this 23 kilowatt long wave from the transmission and distribution line to that community. So definitely, if you are not, if you are minimizing import of electricity, definitely we are minimizing the losses also. And the most important thing is with the standalone micro hydro system, the plant load factor was just 25%. And with the grid connected system, the plant load factor increases to 77%. That is the biggest impact we have seen. And that means revenues increases by threefold. So revenue, actual revenue and expected revenue is plotted in the green bar, and actual revenue is in the red. So this deficit, you can see, this is mainly due to outage of the distribution line. So distribution lines are not very resilient as compared to transmission lines. The outage of the distribution line is much higher compared to transmission lines. So during the outage, the micro hydro system cannot sell electricity into the grid systems. That is the reason of deficiency of this expected revenue versus actual revenue. The same thing is reflected here also. The expected revenue was around 1 million Nepalese rupees, and actual earn is around 824,000 Nepalese rupees. And business model, in fact, this is a utility grid and micro hydro system and load. If currently the utility have this kind of provision, if there is a outage of the grid, this micro hydro system, this generator cannot sell into the load center. This is the one constant we are still facing with the distributed generation, and we are still advocating with the utility that you have your energy meter here in the load center, and also a generation meter here. So even in case of failure of the grid, outage in the grid, let's give the authority to sell this generator into this load center. Definitely this revenue from this household energy meters will be collected by this utility, and this micro hydro systems will be earning money from this energy meter, utility energy meter kept here. So if it is a grid connected, all the power can be fed into the grid system, infinite bus. And if there is a outage in the grid system, some part of power can be consumed into this load center. This is the one constant we are facing. So another thing is that we are also advocating for the power exchange agreement instead of power purchase agreement. So we feel that this for the distributed generation system, PA is a power exchange agreement is a has a better benefit than the power purchase agreement. So it's a similar, if I have to do the analogy, it's a similar kind of net metering kind of thing. PA is simply a net metering. So let me go back again. So what I explained here, if it is a surplus, all the power can be fed into this infinite bus to the utility grid. If deficit, then this generator will supply its own power to this load center, and deficit power can be imported from the grid. So this whole load center will be managed by generator. So it's a kind of power exchange between grid here itself. There will be a net meter, bidirectional meter, and which will account for the both export and import of the energy based on the consumption here in the load. This power exchange agreement shall have some advantage, like RE developer will buy and sell power to the utility. That means buy and sell, both will have a provision. And most important thing is that the utility will not have any burden to manage the distribution of electricity in the village, and also the theft and other kind of non-technical losses will be minimized. And there is no burden of managing this distribution in the rural area, and which will lead to definitely a less O&M and maximize the profit. And if your utility is only supplying electricity to the rural community, the price is maybe monopoly price. So if you are also a power distributor in the village, that means definitely there will be competitive electricity pricing, and you can set your price according to your levelized cost of energy and your profit. And prosumer producer as well as consumer kind of things will be happen in the vicinity. Innovation definitely for the you will be, if utility is there, sometimes we have seen that if there is a outage in the distribution system, it may take around 1 or 2 days to revive the distribution systems. So if there is a power distributor in the village itself, definitely they will be looking for the exporting their generated energy all the time. So they will be managing all the distribution lines, and they will be always looking for the betterment of the service of the distribution systems. And this is one of the provision in Sri Lanka, extended power purchase agreement. In fact, most of the utility in South Asia and Southeast Asian region have a same kind of provision for the distributed generation also, like for the megawatt scale generation. Even in Nepal, the PPA scheme for 100 megawatt and 100 kilowatt hydropower is the same. So you cannot expect to have a same kind of PPA provision. Like a 100 megawatt system, 100 megawatt of hydro system may have several engineers, several technical steps to do all the technical and commercial things. Whereas for the 100 kilowatt of systems in the village, you cannot expect to have this kind of grid impact study and connection agreement and all kind of documentation stuffs from that village producer, village level of power producer. So Sri Lanka has a very good provision having a very reduced format of PPA. So that's a very easy format for the distributed generators like micro mini hydro developers. This is my second last slide. I would like to highlight here the solar provision. This is based on the Nepal case again. So I would like to highlight here some assumptions are given here for the distributed generation, like 5 megawatt, which may be interconnected into the 33 kV of distribution line, and loan equity ratio of 30%, 70%, loan payback period of 7 years, and commercial bank interest rate of 7%, and capital cost of is assumed 804 USD per kilowatt. That's maybe around 5 crore Indian rupees, maybe around 9 crore Nepali rupees per megawatt. This is the assumptions, and all the specific yield, these are the some assumptions. This is a nominal specific yield which can be achieved even in the less sunshine area. So with this, it seems that it is marginally financially feasible with the IRR of 10.28% and NPV value of positive NPV value, and levelized cost of it's around 4 INR per kilowatt hour. It's around 6.5 NPR Nepali rupees per kilowatt hour, or 6 cent per kilowatt hour levelized cost of energy. And sorry, yeah, and payback period is 11.57 years. And in conclusion, distributed generation, as we discussed, has several advantages. Our centralized generation help to minimize the power losses of T&D lines by injecting power near the load center. And definitely it will, if you are injecting power into the distribution line, we have seen that 12 volt voltage boost up is of in the 400 volt distribution system. So that's an increase of the reliability of the grid. And another one thing I would like to again highlight is the inertia constant of hydro is much better than the solar inverters and wind converters, which has a better fault ride through and frequency ride through and low voltage ride through capability. However, one important aspect I would like to highlight here is that if the grid need reactive power during the non-sunshine hour, even in the night time, solar inverter has a capability that solar inverter can export reactive power to the grid even during the night time. That's the beauty of the solar inverter that I would like to highlight for the utility people, that if you are allowing solar inverter to connecting to your distribution system, definitely you will have some kind of beautiful advantage of having a reactive power even during the night time. That means even during the evening time, the peak consumptions happen, and at that time the grid require more reactive power, and solar inverter has a capability to provide during that time. It is not required to have a PV generation. Just having a voltage across the capacitor can have a reactive power generation from the inverter itself. So that's all from my side. Thank you for your kind attention.
Thank you, Jeevan, for the elaborative session that you have took. We'll quickly go through like the questions that we have from the attendees, right? So I have posted one of the question to you, Jeevan. It is from Pushparai. He's asking, in case of solar PV, can we use PEA instead of PPA?
Yes, in fact, as I said that net metering and PA is the same kind of things. So however, the net metering policy and even feed-in tariff policy, these are the not very long-term assurance of the commercial terms. However, this PA and PPA has a long assurance. So definitely the power developer will have a choice of PA instead of net metering. So it again depends upon the how your utility is allowing you. Definitely, if they will be allowing power exchange agreement instead of net metering, it's obviously the choice will be PA. So why not? Definitely, it's a commercial terms. PA is just commercial things. So there is no any constraint. So it's all depends upon the utility. And for the solar also, this PA is also beautiful thing if the utility allows.
Fair enough. I guess the query has been resolved, Mr. Pushparai. If you have any doubts regarding the same, you can put it in the chat box. If we'll be opening this for Q&A session, if any one of you having any question from the webinar, you can put it in the chat box. We'll be putting the question to the to Jeevan, that is our speaker, and we'll get it resolved then and there. Okay, Jeevan, we have another question from Subrat. He's asking, please elaborate more about how reactive power from solar panels can be fed in night time.
Okay, so if you see the topology of the solar inverter, definitely there is a first thing is the DC capacitor link. So if and there will be arrangement of IGBTs. So if you are providing, let's say your solar PV is not giving DC power, and at the same time if you are giving your solar inverter is connected to the grid, that means capacitor link will have also voltage. Okay, so I cannot explain without this diagram. First, I would recommend you go to one literature. Just find the Q at night in the Google. Q means reactive power. Q at night in the Google. You will find a very good document of from the SMA solar inverter. So SMA solar inverter has this literature Q at night. So and if you have if you need more clarification, we can again discuss. So first go through the solar inverter topology and that literature, Q at night literature from the SMA. You will have good knowledge how this reactive power can be injected even during the night time through solar inverters.
Okay, fair enough, Jeevan. We'll take 2 more questions and then we'll be winding up. We have a question of like, what is the purpose of dummy power or powerhouse function from Soumya Roy?
Okay, so I think my screen is still visible. Go
Yes.
through Right. Here you can see the one curve here. Our power. This is a power from this constant line. This is a power generated from the micro hydro system. That is a hydropower. And sometimes, you know, this main load, which is referred to the load connected in the consumer side, that is a village load. So main load, that means consumer load, it is a very time varying things. Sometimes villager can switch on 5 number of lights, sometimes 2 number of light, and there is a multiple number of consumers. So this village load is always varying load. So you have a two option: either just match your generator according to this consumer load through the changing of turbine valve, that means through changing of water flow into the turbine, and generate according to the main load, that means village load. That is one idea. Or another idea is just keep generating constant power and divert the remaining power. For example, if here at this point all the generated power consumed by village, the dummy load. So for this much of power is consumed in the village, the remaining power is green line. This remaining power, this much of height, this much of power is diverted to the dummy load. That means heating of water in the powerhouse itself. So just to balance the frequency, just to balance the power frequency, you have a two option: either by changing the controlling the flow, water flow in the turbine valve, or just diverting generated power to the dummy load. These are the two provisions. So we have incorporated this diverting power to the dummy load because of the economic factor, which I already discussed. I hope I have clarified your question.
So we'll take one more question, Jeevan, from Abhinandan. He's asking regarding the protection mechanism while feeding micro hydro solar PV to the utility grid during grid outage.
Means, Manu, can you repeat question once again?
He's asking about elaboration of safety protection mechanism while feeding micro hydro or solar PV generation to utility grid during grid outage.
Okay, so this is a really good question. In fact, so this power electronics things like solar inverters, these are the very there is no rotating kind of things. So it's for the engineers, for the developer, technology developer, it's a very easy task to manage control and protection functions in the STD generation and no rotating parts. So solar inverters have all the functions, control and protection system. It is our current or our voltage, low voltage, our frequency, low frequency, all the under and over, everything is inbuilt in the solar inverter. Even the rate of change of frequency relay for the islanding protections, rock-off relay, all these kind of reverse power flow, every protection systems are incorporated in the solar inverters. But at the same time, if you are incorporating this control and protection system for rotating machines like microgrid, it's the task become more complex, and it's a really tough task for us to do all this control system for this microgrid system. So we have for this pilot project of this 23 kilowatt systems, we have used from DEIF manufacturer from Denmark. They are very good in control and protection systems of hydro. So there is a GPU hydro, GPU 3 hydro. So we have bought that numerical relay from DEIF manufacturer from Denmark, and they have all provision of this kind of protection systems. We programmed it from the their graphical user interface software, and then we had a several round of calculation and setting changes, and then somehow we managed, and then all the tests were done in presence of utility people or during the testing commissioning time, and then we have checked all the parameters in the testing commissioning. It works well, and then it is still working fine. There is no any nuisance tripping and all undesirable tripping from this control protection systems. Yeah.
Okay, fair enough, Jeevan. I guess like we had addressed like more competitive questions that we had. We'll be winding the webinar now. I have sent you, all of you, the chat message of containing an email where you can get in touch with us regarding more of your questions. We'll get it solved over the email more elaboratively due to the time constraint that we have right now. We have to conclude the webinar as of now. So you can send us the email on student.solarstudy@gmail.com. We'll be more than happy to address all of your queries more elaboratively over the email and get it resolved as soon as possible. Right? And once again, thank you all for being here and attending the webinar on DG in solar PV. And thanks Jeevan for taking this elaborative sessions. And we'll be winding it as of now. Okay? Thank you, everyone.
Thank you, everyone. I hope I have imparted some of my knowledge. Thank you, everyone, for listening us. Thank you so much. Bye-bye. Have a good day.